In this problem, we're given a polyprotic acid and are asked to find the concentrations of several different things in equilibrium. Note that, as with any polyprotic acid, the first donation of a proton is significantly easier than the second or the third donation of a proton. The reason we can say that is because of the extreme differences in the three Ka values they gave us. The first one, 10 to the minus third, is a pretty high Ka value for a weak acid. The second one is on the low side, 10 to the minus eighth, and the third one is extremely small, 10 to the minus 10th. First, let's write dissociation equations, and I'm going to note that we're going to start with the first dissociation, that is, the first donation of a proton to solution. As with any acid dissociation, just write the formula of the acid, an arrow, an H, and then what's left after donating just one of the H's. So H3ASO4 becomes H2ASO4 with a minus charge. We'll write an ice table. And they provided us an initial concentration of 0.23 molar. So that's what gets written in the initial line of the ice table for the acid. Hydrogen and the H2ASO4 ion were not given to us, so we can assume that those are zeros. We'll shift to the side with the zeros. And we can write an expression for the equilibrium of this equation. We'll call this Ka1 because it's the first dissociation. It's always product concentrations over reactant concentrations. And thus far, we're just looking like a normal weak acid problem. I'm going to use the Ka value they gave us, the first Ka value, 5 times 10 to the negative third. And I'll tell you that that Ka value is pretty high among the weak acids, so we may have trouble making the mathematical assumption. We'll make that assumption and then check to see if it was valid. So we're plugging in equilibrium concentrations, and if we go ahead and assume that the expression 0.23 minus x is roughly 0.23, then we have a nice workable equation. In this case, x works out to be 0.0339. Let's check percent dissociation. If we're below 5%, then we were okay to make that mathematical assumption. If we're above 5%, then we've got to go back and redo that equation with the solver feature. To calculate percent dissociation, we take the value of the hydrogen ion concentration at equilibrium, which is simply X, all over the initial acid concentration. Whoopsies. So 0.0339 over 0.23. And in this case, it works out to be 14.7% dissociated. That is above our threshold. The threshold is 5% for making the mathematical assumption. And so we do indeed have to go back and use our solver feature. If you don't like the solver feature, you could also solve this graphically, but we need a more precise value for x. So if we go ahead and use the solver, I'm going to type in this equation in the format 0 equals the equation, x squared over 0.23 minus x. Make sure you don't lose an important set of parentheses. And then we subtract the Ka value, 5 times 10 to the minus third. After entering that into my solver, I get a value of 0.0315, which, if you compare that to the value of x we got by making the mathematical assumption, it is slightly different. I don't know if it's enough to make a huge difference, but the guideline is so long as you're within 5%, you can make the mathematical assumption, and here we were above 5%. Okay, let's jot down what we know. The value of x at equilibrium is both the hydrogen ion concentration and the H2ASO4 concentration at equilibrium, and those numbers are 0.0315. The H3ASO4 we can find by taking 0.23 minus 0.0315, and that works out to be 0.199. We already know several of the concentrations. Let's fill in what we have. The concentration of hydrogen, 0.0315. H2ASO4, 0.0315. The original acid is now down to 0.199. And if we know the hydrogen ion concentration, we can find both the pH and the hydroxide concentration. Let's show work for that. pH would be negative log of the hydrogen concentration. That works out to be 1.5. pOH we can find by subtracting from 14. And the hydroxide concentration we can find by taking the number 10 raised to the negative pOH power. And we're going to get a pretty small number here. That's not surprising, as we got a pretty darn acidic solution. So the hydroxide concentration, 3.16 times 10 to the negative 13th. Notice that we've got 4 of the 6 concentrations they ask for, after only having written an ice table for the first dissociation. You might say, well, why in the world, how do you know that the final hydrogen concentration is 0.0315? Won't the second and the third dissociations add to that concentration? Yes, they will, but because the Ka values for the second and third dissociations are so much smaller, they will not significantly affect that concentration of 0.0315. Let's go ahead and move on to the second dissociation now. There's an important thing I want to show you. We're going to need to have available the equilibrium concentrations of a couple of the species to plug into this next ice table. So we're going to use numbers from the first ice table and plug them into the second ice table. Okay, second dissociation, H2ASO4 yields a proton, and HASO4 as we set up the ice table. It's really important to note that at the end of the first ice table, we had found the concentration of H2ASO4 and hydrogen. Those numbers are going to get plugged in as the initial values for the second dissociation. And the reason for that is this dissociation happens in sequence. We already know that we had 0.0315 concentration for both H2ASO4 and H+, and those will be the initial concentrations in the second ice table. We still have a 0. HASO4 still has a 0 concentration. We'll shift to the zeros. So plus x is on the right side of the equation and a minus x on the left side. And we can continue solving this ice table just like the others. We'll plug in the Ka value they had given us. For Ka2, it was 8 times 10 to the negative 8th. And we'll plug in the other values based on our second ice table. I can tell you with certainty we're going to be safe making the mathematical assumption for this K expression, and the reason I can say that with confidence is the K value is quite small. 10 to the negative 8th is a pretty darn small K value. We'll prove that after we find X. And there's a nifty little thing that happens here. Since 0.0315 plus x and 0.0315 minus x both simplify to 0.0315, we can cross them out. And so x works out to be simply the value of Ka2, which is 8 times 10 to the negative 8th. And that was the equilibrium concentration of HASO4 2 minus. Now we have the fifth concentration that the problem asked us to solve. We had to do that whole ice table just to find one more concentration. Also, I would like to point out that if you're worried about the hydrogen ion concentration changing significantly, well, if we know that X is 8 times 10 to the negative 8th, if we were to work this out, 0.0315 plus 8 times 10 to the negative 8th would be like adding together 0.0000008 to 0.0315. Which is roughly 0.0315. You'd round it to that anyway. So the hydrogen ion concentration doesn't change significantly. With the second, and certainly with the third dissociation. And the same would be true for H2ASO4. Okay, on to the third dissociation. In the third dissociation, we're going to kick off the last proton. And remember that from earlier ice tables, we need to pull values into this ice table. So at the end of the second ice table, we had found that X was 8 times 10 to the negative 8th, and that was the HASO4 2 minus concentration. That is now the initial concentration in the third dissociation. The hydrogen ion concentration we had found after the first dissociation and determined that it hadn't changed significantly with the second dissociation. And so in the initial line of the third dissociation's ice table will remain at 0.0315. The last species, and the one that we have to find in this last ice table, is going to be 0. So we'll shift to the side with the zeros. We'll work out this last expression for K. And because that last K value is going to be extremely small, we will again be safe making the mathematical assumption that X is negligible. All of that is equal to the third Ka value, which was 6 times 10 to the negative 10th, a teeny tiny number. When we crunch that number, X works out to be 1.52 times 10 to the negative 15th, a really, really small molarity. And that would be our last concentration that we needed to find.